All right, ladies and gentlemen, your class recording has started. So, on Monday of this week, we started talking about phase changes, and that started off with this triangle, right, that shows the 3 different states of matter, and then the 6 different possible phase changes that can occur between those different states of matter. And we talked about how phase changes are reversible, meaning that, you know, if that you can get back with what you started with, right? That they are physical changes. You're not changing the actual substance itself. You're just changing some of the properties about that substance. And then we also talked about the idea that some of those phase changes are endothermic and some of those phase changes are exothermic, right? Sometimes we have to add heat to make it happen. Sometimes we have to release heat to make it happen. Yesterday, or actually Tuesday, we then talked about the heating curve and the fact that as we look at a graph of temperature versus how much energy we've added, we see that there are spots where this graph flattens out. And if it flattens out, that means the temperature remains constant. And we said that that is indicative of a phase change occurring. That when a substance is changing from one state of matter to another, there is no change in the temperature of that substance. We're still either adding energy or taking energy away, but the temperature will actually not change. So, this is the heating curve, right? But in your lab from last week, you guys actually made a cooling curve. So, one really big difference, well, there were 2 differences between your cooling curve and this heating curve for water. So first, make ourselves a y-axis and then an x-axis. And on your y-axis of the graph that you made for your lauric acid lab, this was still temperature, and it was measured in degrees Celsius. But then on the x-axis of your graph, yours wasn't energy, it was actually time. And time, depending on how you set up your lab quest, could have been minutes, could have been seconds, really doesn't matter. Okay? All right, then, so that was one change, that yours is time versus temperature, whereas the heating curve that I showed you in class was energy versus temperature, same picture. Then the other big difference was what? How did your graph look compared to that graph? Your graph started high, flattened out, then went low. It might have flattened out again, yes? As most of you kind of saw like 2 flat sections there. Okay? There are 2 flat sections of this graph, and that means we look for relatively flat sections to represent when phase changes were occurring. So, what phase change did you guys see in the lab, just from your observations? Liquid to solid, right? So here we went liquid to solid, right? Now, that happened, and where that happens on your graph, right, if you just sort of backtrack and find out what this value is right here on the y-axis, right, that will be the temperature that your substance went from a liquid to a solid. It might not be an exactly flat area, so you might have to sort of eyeball it a little bit, but there will be an area where it flattens out. And we call that area the freezing point, right, because that's where something froze. It went from a liquid to a solid. If we went opposites, if we made a heating curve for lauric acid, it would look like this. Right? This point right here, notice the red and the blue graphs intersect during that section. Why? Because freezing and melting, which would be the 2 phase changes that we represent there, right, are reversible, right? They're same phase change, but coming at it from one way versus the other way. That's important for us here in this part of the country during this time of year because of that outside, right? All that snow. What's the important temperature that we're worried about for snow?
32.
32 degrees Fahrenheit. Why? Because that's what?
The freezing point.
That's the freezing point. Except tomorrow, 32 degrees will be the what? It will be the melting point tomorrow because we're going to turn all that solid snow into liquid water, right? But it's the same temperature, right? Those phase changes that show up on this, not that triangle, this triangle, right? If it goes from a solid to a liquid, or if it goes from a liquid to a solid, that happens at the same temperature. It's just a matter of, are you losing energy to go from the warm side to the cold side, or are you gaining energy from going to the cold side to the warm side? Okay? Good there? All right. Yes, Andrew?
This may seem like you probably won't be able to answer this question, but can you like draw the heating or cooling code for wood or something?
Say again?
The heating code for wood?
They all look exactly the same. It's just a matter of what temperature do the flat parts
Okay, so
occur.
what temperature would the flat plates be for wood?
Wood usually doesn't go through a liquid phase because it's not a pure substance. It's a mixture of a bunch of things, so it's kind of hard to draw it for like
So
wood.
it's probably like extremely low or something?
Not really. I mean,
for liquid?
like when you go outside, when it's 100 degrees outside, your trees don't start melting, so
Yeah.
the melting point's going to be higher than that. But,
Yeah. Yeah, that would be funny though.
That would-
Or that's fun. That's fun to think about.
All right. Our last part of this discussion dealing with our phase changes is to talk about a phase diagram. So, by definition, a phase diagram is a graph of temperature versus pressure that details the state of matter of a material. So temperature versus pressure that details the state of matter. Back on Thursday of last week, we introduced the kinetic theory of matter. And we said that the kinetic theory uses two factors to tell us the state of matter that something exists. And what are those two factors? What are the two factors that determine the state of matter that something exists in? Together.
How much attraction?
Attraction and movement, right? So how much attraction do those particles have, and how much do they move? What did we say temperature tells us about? So the temperature part of this graph is going to tell us about the movement of those particles. And then you could probably figure out by process of elimination, if the temperature relates to the movement of the particles, the pressure is going to be used to represent what? The attractions, okay? But instead of just relying on process of elimination, let's talk, right? If you had to describe pressure to somebody, how would you do it? When you say, okay, this is the pressure, or this is pressure, how would you describe it? Trey, go ahead.
Two or more forces pushing.
Okay, so we're talking about forces that are pushing, right? And generally we talk about those forces pushing like inward, right? To squeeze things together. Trey, what's going to happen to the volume of something if the pressure increases, usually? It's going to decrease. It gets smaller, right? And if the volume gets smaller because of the pressure increase, right? If those things are smaller, they're closer together. And if they're closer together, generally, what can we say about how strongly they attract each other? They're going to attract each other more, right? So the pressure, by virtue of the fact that it's quote-unquote squeezing stuff together, right, is going to relate to the attractions because squeezing together brings those particles closer. Closer means more attraction. Good there? All right. Let's take a look first at the phase diagram for water, which you have a copy of down at the bottom of your outline. It's a little smaller here. Let's see it all the same. Okay. So it's a graph. And hopefully we know from math class, right, your graph has two axes, right, an x-axis and a y-axis. So if we look, temperature is being related on the x-axis, right, degrees Celsius, and then pressure is on the y-axis. Now, pressure is in a unit that we call ATM, or it's labeled as ATM. It stands for atmospheres. That's the pressure that normal substances feel at sea level. So we kind of think of that as like normal pressure. But the pressure here on Earth changes, especially with elevation. What generally happens to the pressure as we go up to higher and higher elevations? Do we we know in general what happens to the pressure? No. As we get higher up, higher elevations, the pressure decreases.
But like when you're in a plane, does it like when you as you go up higher, your ears start turning?
They do, because there is a pressure change. Now, that's more because of the pressure, like there's pressure inside of your body, and if it's different than the outside, the pressure will either push out from inside of you or will push in from outside of you. Does that make sense? So there are some changes there, but then they pressurize the plane to make it more like what we feel down on Earth. Does that make sense? Okay. But as you go to higher and higher elevations, gravity pulls the air closer to the ground. We don't think of gravity generally as acting on air, but it's matter. And so gravity actually pulls the air closer to the ground. So there is more air in this classroom than there is like in a classroom in Denver, Colorado, because the elevation is higher. There's physically more air particles in this room, and that relates to more pressure. Does that make sense? Catherine, are you okay? Good.
Yeah.
Okay.
Wait,
Christine, go ahead.
is that why like when there's a fire you're supposed to, or is that why when there's a fire you're supposed to like go to the ground because there's more?
That's more along the lines of because the smoke usually is hotter than the air in the room, and so it rises up. We'll talk more about that in the next section. We talk about like convection and stuff like that. So that smoky hot things from the fire, they generally go upward because they're hotter, not so much because it's different pressure. But that leaves the cooler, cleaner air down at the bottom, and that's why you're supposed to go up. That's more of a convection thing. We'll talk about that next section. Okay. More good.
And like when you like are like in like the ocean or like in the lake and you like dive down to get something, how you have to like plug your nose
Yeah.
and like
Because
that's like get your
two reasons there. One,
what?
no, it's perfectly fine. One, liquids are going to apply more pressure than gases are anyway because there's more particles. You know what I'm saying? The thicker something is, the more pressure it would apply, like to your body. But also, too, the deeper and deeper and deeper you go, the more pressure there is because of that same gravitational effect, and because you have more water like pushing down on you. You know what I'm saying? If you go off of a diving board, right? The depth of the water in the pool is anywhere between like 10 to 15 feet. You know, the deeper you go, the more water there is like pushing on you, so you feel it like in your ears and in your nose and stuff like that. But if you go deeper and deeper and deeper, like into the ocean, you go like a mile down, 2 miles down, there's so much water there that the pressure is so great that your body wouldn't be able to withstand that pressure, that it would start like collapsing in on itself, just like you pushing a balloon from the outside. Does that make sense? Like you can push on a balloon and squeeze it.
You would like collapse from the.
Just wait.
There's a myth.
Is there a video?
Did it work?
No, they put him in like a suit and they just saw how far they could get him down and it like shriveled up into like the top of his, like it was terrible.
Oh, just wait. We got a good example coming up here on that. So, okay.
A video of a person.
Not a video.
Yeah, we're gonna watch a video of a person.
Trey,
like,
this discussion is actually better if you just picture it as opposed to me showing it. All right, but the important part about this phase diagram, is that phase changes depend on two factors, temperature and pressure. Here, we think about phase changes only requiring changes in temperature, that if we heat something up, it will melt and eventually boil, and if we cool something down, it will condense into a liquid and then eventually freeze. But there are really two competing factors there, and depending on what the pressure is, that will affect the temperature. For example, this graph is split up into 3 sections. The red lines, or the maroon lines, whatever you want to say it, those lines are the boundaries between those different sections. And you notice that the 3 sections are labeled solid, liquid, and vapor. Okay? So you take a look at the pressure in a certain location and the temperature, and that will tell you what state of matter something exists in. For example, here, we're pretty close to sea level. So our pressure is just a little less than 1. So I'll draw this dotted line right underneath that 1 atmosphere line, because that's like sea level. That's normal atmospheric pressure. Okay? And the temperature in this room is about 20 degrees Celsius, give or take. So on the temperature axis, here's 0, here's 100, right? 20 would be, I don't know, this range right here, right? Does that make sense? Yes, it? And so I draw the arrow, and they intersect at this point right here. What region is that on our graph? It's in the liquid phase, right? Because water exists as a liquid in this room at this temperature. But if we put it on the hot plate or we heat it up with the Bunsen burner, that's going to affect the temperature, right? So which arrow do I have to move, red or blue? Blue, right? And I'm going to move the blue arrow which way? To the right. So it goes up, 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 boom, right? That's where they intersect now. That point right there. If we look, that's right on this line, right? That line is the intersection between which two states of matter? Liquid and vapor, right? Or liquid and gas. So if we're right on that line between liquid and gas, what is that water doing?
Boiling.
It's boiling. It's turning into a what?
Vapor.
It's turning into a vapor.
Good morning. One quick announcement. Thank you, Mr. Egan.
That line represents the transition between liquid phase and gas phase, so it's boiling. If you have ever looked at a box of like Rice-A-Roni or Hamburger Helper or something like that, okay? There are directions on it, but then right underneath the directions there are high altitude directions, okay? As we just discussed, Maura, when we go to high altitude, what happens to the pressure?
It decreases.
It decreases, right? So Maura, which line am I moving, red or blue now?
Red.
Which way?
Down.
Down. So notice, if I move the red line down, right, if I don't change the temperature, my water isn't boiling, it's actually already what? A vapor. But before it turns into a vapor, it has to do what?
Boil.
It has to boil. So we slide this blue line down, and we intersect them here, which is still on the line, meaning that the water is still doing what? Boiling. But is it boiling at 100 degrees Celsius?
No.
It is not. It is boiling at a temperature lower than 100 degrees Celsius.
So is that if like you're boiling, if this is possible, I know it's not, but is that like if you're boiling water like underwater?
That would be more if we went this way, right, Maura?
Oh yeah.
Right?
So that's like you're boiling water like on an airplane, like
Yeah.
outside.
Yes.
You're on the,
Yes.
like on the wing.
Or just like say like in like, or more just say like in your kitchen in Denver. Okay, right? That's there we go.
I like the boiling out on the wing.
It's like the boiling point of water is 100. That's relative. Like it's like when you're at sea level. That's
Phase changes are not exclusively a temperature thing. They're also a pressure thing. Okay? Meaning that we could, in theory, take the pressure down, let's say here. Okay? Sorry, Trey, we didn't get to the cool part. Hey, whoa, hey! Hey, you guys have a quiz you have to take with you?